Okay, lesson 8.5, constant rate of change and direct variation. We'll spend just a few minutes on constant rate of change, and then the bulk of the time we'll spend talking about things that relate to direct variation. Basically, we're only spending a couple of minutes on constant rate of change because it really just kind of finalizes what we've talked about the last couple of days with rate of change. And we've even talked about the fact that straight lines have constant rates of change. The rate of change doesn't alter from one set of points to the next. So if you find the rate of change for any two ordered pairs on a line, you found the rate of change for the entire line. It's not going to change from one point to the next is what that means. So if we find the rate of change from here to here, we found the rate of change for everything on that red line. Does that make sense? And if we find the rate of change from here to here, we found the rate of change for everything on the blue line. We talked about that a lot yesterday when we went through the assignment, and I kept kind of bringing home the point that it doesn't matter what two ordered pairs you pick, right? You can pick any 2 points on the line and find the rate of change. And that just illustrates the fact that there is a constant rate of change. A couple of things about rates of change. They can be positive rates of change, show a positive relationship, or they can show a negative relationship. And then here's a couple of examples of things that would not be constant rates of change. Every now and then in your assignment they might throw something like that in just to show you that there are other types of graphs out there. And obviously these are not linear functions, they're not straight lines. And since they're not linear, then they would have differing rates of change. And what that means is from this point to this point, there would be one rate of change, but that's going to be way different than the rate of change from this point to this point. Does that make sense? Yeah. Okay. So constant rate of change, you just need to be aware of the fact that when you're working with a straight line, it's going to be a constant number. It doesn't change from one point to the next. That's all that means, okay? Everybody with me? Yeah. Now, let's move on and kind of bring in some things that we talked about back in chapter 6. In chapter 6, we were talking about proportions, and we're going to talk about proportions in terms of some of the relationships that we'll look at with linear functions. Some linear relationships are proportional. And if you remember back to chapter 6, what did we do with a table of information to show that it was proportional? Simplify. See if it simplifies to the same rate. And since we know where time goes when we're working with time, where does it go on the ratio? Bottom. Time goes on bottom. So we'll set these up with the y over x, distance over time, 4 over 1, and that doesn't reduce, and then 8 over 2 reduces to 4 over 1, and 12 over 3 reduces to 4 over 1. So we have shown that this relationship is proportional. And here's a graph that shows that it's proportional, or that shows that it's a linear function. And what is the rate of change formula, by the way? Austin?
y2 minus y1 over x2 minus x1.
y2 minus y1 over x2 minus x1. And so do I have some ordered pairs on this table here? Yes, absolutely. I have an x value, I have a y value. And so I can use any 2 points to find the rate of change, correct? Mm-hmm. And I will use any 2 points. So 1, 4, and 2, 8. Those are my 2 ordered pairs. And right here, in this little box, I'm running out of room, but right here I'll find the rate of change for this linear function. So that would be 8 minus 4 over 2 minus 1. 8 minus 4 is 4, and 2 minus 1 is 1. What do you notice about that?
It's the same as the proportion.
It's the same as the proportion that we used to show that it was a proportional relationship. Okay? And so the rate of change, it turns out, is the same thing as this proportion that we use. Here, what's that?
Is that always going to happen?
Hold on to that thought. We're gonna see, because that's kind of an interesting discovery that we're on the verge of making here. So before we move on with proportional relationships, let's take just a minute to look at this. Some linear relationships are non-proportional. And non-proportional linear relationships How many do I have to show are non-proportional before it, on the last one, I had to do all three of them to show that the graph was, or the table was proportional.
They don't, first two don't match, then you don't even have to.
If you find two that don't match, then you're good. So, again, let's do y over x, so it's 4 over 1, does not reduce. So then we'll do 6 over 2, and that reduces to 3 over 1. So what have we just shown?
That it's not proportional.
It's not proportional. But look at the line on the graph. It's still a straight line. And so even though it's not proportional, it's still a linear function. And all straight lines have constant rates of change, right? Okay, so we can still find the rate of change. We find the rate of change by taking any two ordered pairs, so 1, 4 and 2, 6, and use our formula, y2 minus y1 over x2 minus x1. So 6 minus 4 is 2, and 2 minus 1 is 1. Okay? And that would have worked for any set of ordered pairs that we chose on this line. So it still has a constant rate of change that's going to work with any two ordered pairs. But it does not have a number that shows that it is proportional because it's not proportional. Okay? Does that make sense?
Yeah.
So every line will have a constant rate of change, but not every line has a number that shows it's proportional. Okay. Let's spend some time talking about proportional relationships, proportional functions. Just be aware that not all of them are proportional. Some will be lines that have a rate of change, but they don't have anything else we can do with it. Okay? So here we go. Determine if the relationship of distance to time is proportional. Now where does time go? On bottom. So let's set up our ratios properly. So 90 over 2 equals, you might need your calculators for some of these. That's going to be 45 over 1. And then 225 over 5 equals 45 over 1. And 270 over 6 equals 45 over 1. And then 360 over 8.
45 over 1.
Okay, you remember this whole process from back in chapter 6 when you had to check everything on the table to make sure it was proportional, right? Okay. Well, and with this, even without a graph, could I find the constant rate of change?
Yeah.
Because I have ordered pairs here on the table, right? So with just the information on the table, we could find the rate of change. And the rate of change, pick any two ordered pairs. 290 and 5 and that means y2 minus y1 over x2 minus x1. 225 minus 90 is going to be 135, right?
Mm-hmm.
Over 3, and what does that equal? 45 over 1. So what have we seen about the rate of change and this number right here? Okay.
So if it's proportional, it'll be the same. Like it'll be the same.
Okay.
But if it's not, then it's still gonna have what you call it.
It's still going to have a rate of change, but it's not going to have this number. Does anybody, by the way, back in chapter 6, we had a name for this number when we found that something was proportional. Does anybody remember what that was? If you don't, that's okay. We'll get to it in a minute.
Wait, a name for something that's proportional?
A name for the relationship when things are proportional. It was a special name that we called that.
Function?
No, we weren't talking about functions in chapter 6.
Can I look?
Look in your notes real quick. Take a second look, see if you can find your chapter 6 notes. When we're talking about proportional relationships, should be like unit 3, maybe 4.
3, 30, 6, 4, 6, Stop looking at your own. Constant of proportionality?
Yes! Constant of proportionality, good. And so, this is the constant of proportionality, and this is the constant rate of change. Turns out they're the same number. So if it's a proportional relationship, then the constant of proportionality will be the same as the constant rate of change. Okay, what letter, by the way, did we use for constant of proportionality? Anybody remember that?
Okay.
K, that's right. So we found K here. K equals this. And this, we really didn't give a letter to constant rate of change. That comes later. And we'll talk about that in a future lesson. But constant of proportionality, we talked about K. So let's kind of bring some of this stuff together then. And by the way, this next slide, we've got the same information as was on the last table. But it's I mean, we know it's proportional now, so we don't have to go through the steps to show it's proportional. But now I want to see what this looks like on a graph. So let's graph it real quick. You've got 290 and 5, 225, 6, 270, and 8, 360. And then since we're graphing a linear function, we need to make sure that it goes through the graph. Okay, so, all right. That's pretty close. All right, that's good enough. Now, I want you to think about all the things that we've just talked about. First of all, the constant of proportionality turns out was the same as what?
The constant rate of change.
The constant rate of change. Okay? And so this graph actually shows that the constant of proportionality is the same as the rate of change. We could use any two ordered pairs like we did and all of those things. I want you to spend I'm going to give you about 15 seconds here as soon as I'm done talking to just look at this graph and note as many details about the line on this graph as you can store up in your memory. Think about its shape, think about where it's going, about what numbers, think about what it looks like. Okay. Go. All right. Now, as we move on and talk about a little bit more about proportional relationships, I want you to see if you could notice a pattern or notice something about the next graph that we look at as it relates to this graph, okay? So, the graph shows the cost of different amounts of trail mix. Determine if there is a proportional linear relationship between the cost and weight of the trail mix. Okay, it's obviously a linear relationship because it's a straight line, but is it proportional? That's the question. Now back in chapter 6, when you had a table of information, you had to check every piece of data on that table to see if it was proportional, right? Well, now you're given a graph. Is it even possible to test every piece of data on a graph?
Well, it is with tape.
It would take an awfully long time because this line tells us that it keeps going on into infinity. There are numbers in between the vertexes here where they meet. Can we possibly check every single number in existence to see if they're proportional on this graph? That would be really, really tough. And so to show that it's proportional, we have to do something else with graphs. What did we find out were the same when we were checking the other one for proportionality? Okay, so if we show that the rate of change is the same thing as the constant of proportionality, then we have proven that it's a proportional relationship, okay? And so what we need to do is check to see if there is a k value. And k was a simple matter of y over x. All we did was take a y value and put it over an x value. So can we come up with an x and a y value on this graph?
Yeah.
Okay, give me an ordered pair.
2, 7.
2, 7. Okay, so y over x, then k would be, if there is a k value, k would be 7 over 2. Okay? Now let's check for a rate of change. How many ordered pairs do I need to find a rate of change? 2. I need a y2 and a y1, and I need an x2 and an x1. I already have one ordered pair, so I need another one.
414.
414?
Yeah, 414.
414. So y2 minus y1 over x2 minus x1. And that is going to be 14 minus 7 is 7. 4 minus 2 is 2. So what do I notice about the rate of change and the k value?
Same.
So what does that mean? It's a proportional relationship. Okay? Now, I asked you to take special note of the shape of that last graph and then compare it to this one. Do you notice any similarities?
They both run through the origin.
Yes! That is exactly the thing I was hoping you would figure out, the thing that I was hoping you would observe. It goes through the origin. Here's the deal. There is a special type of linear function that goes through the origin. It is called a, what was the title of your lesson? Constant rate of change and direct variation. Okay, direct variation equations will, or direct variation functions will always go through the origin, and they are always proportional. Okay?
So if it goes through the
So,
origin, it's always proportional.
If it goes through the origin, then it is proportional. And if it is proportional, then we have just discovered a very important fact. What do we discovered about things that are proportional?
They have the same constant rate of change?
Yes, the constant rate of change and the constant of proportionality are the same thing. So if you know it's proportional, because it goes through the origin, how many ordered pairs do you need to find the rate of change? One ordered pair. Because all you have to do is find the k value. If you find the k value, you've got the constant of proportionality. Right?
0.
Okay. Whew. All right. Now, let's look at, and in this lesson in the book, it changes. Sometimes they use different terms based on the lesson they're using, and in this chapter, they're using, instead of saying constant of proportionality, they're saying constant of variation, because we're talking about how y varies according to x. So as x changes, what happens to the y value? That's what rate of change is all about. So it calls it constant of variation instead of constant of proportionality. But it's the same thing. Okay? Now, constant of variation is k equals y over x. And all we need is how many ordered pairs?
1.
1. Since we see that this line touches the origin, goes through the origin, I only need one ordered pair to find the rate of change and the constant of variation. They're the same thing. So give me an ordered pair.
0, 0.
Oh, can't use the origin.
1, 2.
You can't, awesome. Yep, you can't use the origin because then you would only have 0 over 0 and that doesn't give you what you want.
Wait, I
Okay.
thought we're supposed to.
Well, if it goes through the origin, that tells you that it's proportional, but you can't use the origin as your point to show the constant of proportionality.
Okay.
Because that would just be 0 over 0 and that doesn't tell you anything.
Did you simplify or whatever?
Okay, so k equals what?
2 over 1.
2 over 1. So that is the constant rate of change, the constant of proportionality, constant of variation, all the same thing. Okay? Yes.
So we only have to do that basically for
That is the rate of change, that's the constant of proportionality, that's all those things wrapped up into one, yes.
Oh.
So whereas yesterday, if we were doing this line yesterday, you would have had to have 2 points to do the y2 minus y1 over x2 minus x1, right? Today, you don't need 2 points because you know it's proportional, you only need 1 point. Okay, does that make sense? All right, now the other thing, there was another way that we used this direct variation or constant variation equation, k equals y over x. Does anybody remember another way that we wrote it?
y equals k times x?
Yes, y equals kx. Okay, and so there will be occasions when you want to use this to find out, you know, once you have the k value and you want to find out how many miles you're driving or how much it's going to cost or what the total number is going to be, then you'll want to use the equation this way. To find out what the k value is, it's just y over x. And then once you have the k value, you'll use it in an equation like this usually. Okay? All right. let's do a quick recap of the lesson. I feel like we've kind of absorbed a lot of stuff today. Number one, all linear functions have constant rates of change. This is like the rallying point. This is the fallback point where it's always going to work. If you don't know if it's a proportional relationship or not, you don't have enough information, you can't see all of the graph, they give you the stuff in table form, whatever. If you don't know if it's proportional, this will always work to find the rate of change. So you can always use this formula, okay? If you do, though, some linear functions are proportional. So if you know it's proportional, then there's some other things that we learned. If you know it's proportional, then it's called a direct variation, and its line will pass through the origin. So if you're looking at a graph and you can see the origin line goes through it, then you know it's a direct variation. That tells you some things about the relationship. It tells you that it's proportional. It tells you how you can find the rate of change, those kind of things.
So no other, like, linear function, if it doesn't go through the origin, then it's not proportional? Like,
Yes. If it doesn't go through the origin, it's not proportional. It's still linear, still has a constant rate of change. That's when you'll use this formula for sure. If it doesn't go through the origin, you have to use this formula, okay? If it does go through the formula, if it does go through the origin, then you can use the k equals y over x formula. And then if it's a direct variation and you have to find some other piece of information, you can use the y equals kx formula, okay? So like there wasn't a whole lot of new stuff in today's lesson. It was just like bringing a whole bunch of things that we already knew together into kind of one spot. All right, let's look at the assignment for today.
okay,